My name is Mr. Jern, and this is Principles of Engineering 1.1 Mechanisms, Simple Machines, Part 2. Part 1, we talked about the lever, we talked about mechanical advantage, we talked about the lever, we talked about the wheel and the axle, and we talked about the pulley. Well, today we're going to wrap that up because we have the three other simple machines: the inclined plane, the wedge, and the screw. So these are, remember there are 6 simple machines, and these are just the second three of that bunch. So the inclined plane, wedge, and the screw. So first, a quick recap on mechanical advantage, or MA. Remember, this is the ratio of the magnitude of the resistance and effort forces, as well as the ratio of the distance traveled by the effort and resistance forces. So basically, it's always a trade-off. If you want to make something easier to require less force, then you're going to have to increase the amount of distance. And the reverse is true. If you want to decrease the amount of distance, then you're going to have to increase the amount of force, okay, using these simple machines. So these ratios allow designers to manipulate things like speed, distance, force, and function of things. So it's pretty useful in engineering. So we gave the example of this 4-to-1 mechanical advantage on this inclined plane. So what does it tell us about this? Do you remember? Well, it basically tells us that the magnitude of the force, the effort force, that red arrow there, where'd it go? That red arrow is going to be 4 times less than the magnitude of the resistance force. So we are lifting this yellow block up, and so what's resisting that? Well, that's gravity is resisting that. And so the magnitude of the resistance, which is going to be the blue arrow here, is going to be decreased by 4. It's going to be 4 times less effort to lift it against gravity. But it also means it's going to be 4 times greater the distance. So that's the trade-off. So remember, 1 is the magic number for mechanical advantage. And basically anything that's greater than 1 is going to require proportionally less force, but it's going to require greater distance. If something has a mechanical advantage of less than 1, then you will get it will require a greater force, but it will require less distance. Okay. And just remember that mechanical advantage can never be less than or equal to 0. It's a ratio. So then we have our IMA and AMA. Just a little recap again about this, and we're going to get into this a little bit we're going to see it in action. So ideal mechanical advantage is totally theory-based. There's no friction involved. It's all computation. Friction loss is definitely not taken into consideration. It's all about comparing the distances, which is going to be one of the main aspects of mechanical advantage. And so the ideal mechanical advantage is just the effort force, the distance of the effort force, divided by the distance of the resistance force. I am a deer. All right, I am a deer. IMA is equal to dE over dr. In contrast, the actual mechanical advantage, or the AMA, is calculated by taking measurements. So the IMA is there's measurements of distance, but in this case, measurements are taken of the actual forces required to move things or to do the work. So in this case, frictional losses are taken into a consideration because it's happening in real life. It's inquiry based. It's like inquiry. I have a question. How is this actually going to work? Let's actually do it and try it out. And we're going to use this for efficiency calculations, which we talked about too. And in this case, the AMA is the magnitude of the resistance force divided by the effort force. So it's just how much resistance are you trying to overcome divided by how much resistance, how much force do you actually have to apply in effort. So one of the simple machines is an inclined plane. We've already kind of talked about this. This was our example. But to define an inclined plane, it's just this. It's a flat surface set at an angle or an incline with no moving parts. Okay, it's a ramp. You're able to lift objects by pushing or pulling on the load. So we have our famous example that we talked about a million times. We've got other inclined planes. I'm sure you could think of a million of them, including roller coasters. Okay, And to figure out the IMA, it's still the DE over the DR, the effort distance divided by the resistance distance. And in this case, the effort distance is the difference traveled by the effort. In other words, you're pushing something up a ramp. What is the distance you had to push it or pull it? And that distance is parallel to the slope. This little symbol here means parallel to. So parallel to the slope, how far is this thing traveling? That's the effort distance. The resistance distance is, well, the distance traveled by the resistance. In this case, how high up are you going along the ramp? Because that's really what we're trying to do with the ramp, is to lift something. And so we lifted up this distance. So what is the IMA here? Well, it's going to be the length divided by the height. And so to calculate this, the IMA of this inclined plane, we're going to have to take our length, which is 15 feet, divided by the height, which is 4 feet. The feet will cancel out. We're left with 3.75. So we kind of round that a little bit, and we get a ratio of 3.8 to 1. So that's kind of nice. It's a pretty decent IMA. But now, what is the actual AMA here? Well, we actually have to do it and try it out. And it turns out it's going to take 20 pounds of effort to lift this 50-pound cart here up to 4 feet. And so it's kind of nice because I'm lifting a 50-pound object using only 20 pounds. That's the nice thing about MA, mechanical advantage. So let's see what the actual mechanical advantage is when we try this out. So we take our resistance force, the 50 pounds, that's our resistance, 50 pounds of resistance, divided by our effort force, 20 pounds of effort force. The pounds cancels out. So we're left with an actual mechanical advantage of 2.5 to 1. Yeah, that works. Nice and easy, just division. Okay, but now the useful thing is, how well did this ramp work? Well, what's the efficiency of it? Well, we take efficiency, which is something we talked about in the last video, and we take our AMA divided by our IMA, multiply it by 100, and in this case, we do the division, 2.50 divided by 3.75 times 100, and we get a 67% efficiency. Okay, not bad at all. Some friction involved, definitely. So that's an inclined plane. Now, the next one is a wedge. A wedge you probably have seen a million times, or you probably could picture it. It's exactly what it sounds like. It functions as a moving inclined plane, okay? It tapers to thin edges and is used for splitting, raising heavy bodies, for tightening by being driven into something. So things like shims, well, obviously wedges to split wood, and other things like that. The axes are all, well, you can see this would be a wood splitter type of thing. Axes are wedges, hatchets, those kinds of things. Even the cutting edge of a knife can be considered a wedge if you're just kind of pushing directly down into it. Okay, so you get the idea of what a wedge does. It pushes downward. You apply a force down, we'll just say downward, it could be any direction, but you apply a force one direction and it applies a force. The resistance force is basically usually perpendicular to that. So to figure out the ideal mechanical advantage, it's the same formula. What's the effort distance divided by the resistance distance? And so to figure that out, well, which of these is which? So to think about that, the effort distance is the distance traveled by the effort. All right, so how far do you have to push this thing down in order to get it to do its work? All right, well, if we want to do the job the entire 3 inches of the wedge, we're gonna have to push this thing down all the way 10 inches into the thing we're splitting, the wood or whatever. So that means the resistance distance is the distance traveled by the resistance. In this case, like if we're splitting wood, that wood is gonna get split 3 inches, okay? But we had to push this wedge in there 10 inches to do that. So again, we get a trade-off of distance in order to do work, which would be pretty difficult to do without this. So the IMA here is the length divided by the height, and now if you know anybody who's into engineering, there's some caveats here. There's a little bit of debate here, but I don't want to get into that. We're just going to go with this. But I just want to acknowledge that if you take some advanced engineering classes later on, you might see an alternative way to do it. It's sort of in dispute, but we'll just stick with this. So don't even worry about that right now. So you're going to take the length, which is perpendicular to the height, okay, The height, now this is a little confusing because you're like, well, wait, height is usually up and down. Just, this is how it is, unfortunately. It's because you think of height as, think of it as like they're sideways, it's two inclined planes put together, right? So the height is that, well, the height of an inclined plane. So think of this as two inclined planes stuck back to back, and now they're turned on their side. We still call it a height. It's just how it is. So we take that length of that's going in divided by the height that is being split apart. So the IMA here is the 10 inches divided by the 3 inches. So we get a ratio of 3.33 to 1. Now, we actually do it and we split the wood or whatever, and we find out that it takes 250 pounds to push with 700 pounds of effort, okay, in either direction. And this is Newton's third law, where equal and opposite forces. So we're only going to count the 700 pounds once. And so let's take a look at how we do this. The AMA on this wedge, you take the resistance force, which is 700 divided by the effort force, 250. Okay. And like I said, we only count it once because it's only, it's just how it goes. You only count one of the 700s because it just takes 700 pounds to separate the two. We'll just think of it that way. It takes 700 pounds to separate the two. So the AMA is 700 divided by 250, which is 2.80 to 1. Okay, again, we find the efficiency here. So the percent efficiency is the actual mechanical advantage divided by the ideal mechanical advantage, and we do the multiplication. We get an efficiency of 84%. Not too shabby. All right, let's talk about screws. It's our last simple machine. There's 6 of them. Screws are a little complicated. They've got 2 components. We got an inclined plane wrapped around a cylinder, which forms the path and the pitch. So there's a couple names here. Specifically, the pitch is one of these words you're going to want to kind of just keep in the back of your skull. It's also a wheel and axle used to create rotary motion. So you could visualize the plane, the inclined plane, but then during the action of the screw, it becomes a wheel and axle. So there's a couple things to keep in mind here. All right, so when you're considering the IMA of a screw, we're going to focus mostly on the inclined plane part of it, the threaded part, because if you use like a fatter screwdriver or a wrench with a longer handle, well then, a shorter handle, that's going to change the wheel and axle component of your machine. So let's just focus on the screw part. So what a screw does is it changes rotary motion into linear motion. If you have a screw, you're turning it, you're twisting it. That's the rotary motion. And so what that's doing is, why do you do that? Well, you want it to go down. You want to go into something or out of something. And so you're changing like a spinning motion into a linear motion. That's the purpose of a screw. It can be used as it's a threaded fastener. Obviously, you can fasten things together. It has a very large mechanical advantage. We're going to see that in a minute. But there is a very large amount of frictional loss. I mean, if you ever tried to screw something in, you know how that is. So, really quick note about screw identification. These are very standardized. It's very standardized. If you were to look up 1/2 13 NC on the internet, you would find a specific screw or bolt. And so a couple things. First of all, this thread information, when you find it, the first thing noted here is the diameter of your screw, of the screw part of the screw, not the top part, not the effort part, but the actual screw part. Okay, measured to the outside. So 1/2 inch diameter in this case. Threads per inch is the second number. And that just means, like it says here, if there's 13 threads per inch, which is the case here, then that means the pitch is 1/13 of an inch. Okay, what that means is there's literally, if you were to take a ruler and measure 1 inch of this screw, you would count 13 threads. NC stands for, well, in this case, it stands for coarse. There's also NF and a couple others. You don't have to memorize that or anything like that, but this is just a thread description. Is it coarse or is it fine? So NC is coarse, NF is fine. And like I said, there's a couple others. We're not going to have to worry about that. Okay. Now, looking into, pitch is one of the words I mentioned earlier. It's just a distance between the threads, nothing more. It also, because it's the distance between the threads, It is the distance that the screw will travel linearly when you rotate it one rotation. So in other words, when you rotate a screw once around, it's going to go into, let's say, wood or metal. It's going to go into the wood this distance, the pitch distance, okay? Let that sink in a second. Then we got our effort arm distance. If using a wrench, this is where it gets a little like blurry, I guess. If you're going to use a wrench or a screwdriver, obviously you're going to have to take into consideration the effort arm of the tool that you're using. Because if you tried to just turn this by your fingers, you could do that, and then you wouldn't have to worry about a couple other things, right? So the question is, how far will a screw with 13 threads per inch move linearly if it's turned one full rotation? Well, the answer is 1/13 of an inch. Okay, you would have to turn this thing 13 times in order for it to go down 1 inch. That's just what this means. All right. So let's talk about the IMA, the ideal mechanical advantage. Still going to be the effort distance divided by the resistance distance. But like all these things, it's the identification of what's what. That's going to be the tricky part. So the effort distance might not seem obvious, but it's the distance of one rotation of the effort arm. It's going to be the circumference of the screw. All right. So that's going to be the effort distance. The resistance distance is how far does the screw travel in that one rotation. In other words, it's going to be the pitch of the screw. So the way to find the IMA of a screw is to take the circumference divided by the pitch. So you need to know the pitch, which fortunately is given to you in the identification of the screw. And 2 pi r, well, that's also given in the identification of the screw. So in this case, we have an 18-inch long wrench, or 8-inch long wrench to push this in. Ooh. So this probably could have been a little bit more clear, but let's take a look here. It all popped up at once is all. So the IMA, the ideal mechanical advantage, it's going to be 2 pi. We got that, 2 pi times r. So the radius is going to be an 8-inch long wrench. So you hook up a wrench to this, it's going to be 8 inches long. Okay, so forget that 1/4. That's if you're turning it by hand, I suppose. You use a tool on this, and so the radius is 8 inches long because you have an 8-inch long wrench. Divided by the pitch, well, that is definitely given. So it's 1/20th, like I said. You get that information from right here. So 1/20th, 1 inch is over 20. So you take 2 times pi times 8 divided by 1/20th. That's going to give you this number right here. And so our IMA is going to be basically 1,000 to 1, right? 1,000 to 1, 1,005 to 1. The AMA, you're going to have to do the measurements again. You're going to take a measurement forces or force measurements. So the resistance force divided by the effort force. So in this case, we have a effort force. You're trying to push. It takes 2,000. Like if you wanted to just drive the screw into the wood or whatever, the bolt into the metal, you could, but it would require 1,200 pounds of force to do that. All right. So if you wanted to just use a tool and get it done easier, it's going to take 35 pounds of force to actually just turn it in. So you can see why this is super handy. So we take our resistance force, 1,200, divided by our effort force, 3,500, and we get our AMA of 34 to 1. What's the efficiency of a screw? Well, now that's another story. Our AMA divided by our IMA is our 34.29 divided by our 1,005.3 times 100. So our efficiency is only 3.4%. And there's a lot of friction in a screw. But that's basically it. Oh, why is efficiency so low? I guess I just answered that. Did you catch what I said? All right. Finally, just a little recap, because compound machines are everywhere. You don't usually see like one. I could probably see about 3 or 4 machines just by glancing at this thing right here. All right, see how many you can find, because there's a lot of machines going on, simple machines. So remember wheel and axle and all that stuff like that. And to calculate the total mechanical advantage of a machine like this, you would just multiply the mechanical advantages. So that's it for the compound machines. And if you have any questions, of course, like usual, just please let me know. Have a good day.